Well, you did right. I just okay.
Yeah, I think that's
Okay. I think we're ready. Thank you. Welcome to the CQuiC seminar. So today, it's our pleasure to welcome Josh Crackers from Sandia National Lab. Josh's work revolves around the problem of simulating large physical molecules and using systems like machine learning and other tools to do stuff to do that. He got a PhD in biophysics to the University of St. Louis in 2019, and after that, shortly after that, he joined Sandia here in Albuquerque as a Harry Truman Fellow. So, welcome, Josh.
Thank you. Thanks everyone for coming. It's a ton of fun for me to get to talk to you, and I have already spoken to some of you today, and I appreciate the broad range of expertise that's in the room. So feel free to ask me questions anytime you want. It's supposed to be informal. So because I'm new to most of you, I think I start with a brief introduction. So I grew up in Ohio and went to Ohio State University for undergrad, right? Majored in physics, so probably many of you in the room. And didn't know that I wanted to go into being a scientist right away. So I took some time and I became a high school teacher. So I taught in high school physics and chemistry in inner city Baltimore, Maryland for 3 years. And this is a picture that always makes me happy to show. This is a picture of my very last class of graduating students. I guess half of the last class, equivalent picture of the girls in the class. And there's a funny story I like to tell about this young man, Christian, down here in the corner. So we're all in class one day, and Christian's like working on something. And he was always the sort of kid that was really tough to get motivated to really work hard on physics. And so he's like working away at his worksheet, and he shoots his hand up out of the middle of the air. And I call him and I say, "Hey, Christian, what's up?" And he goes, "Mr. Rackers, you're always telling us that we should care about physics because we can use it to solve problems in the real world, right?" And I go, yeah, Christian, I do say that. And he just kind of looks at me and goes, "Mr. Rackers, why don't you do that?" I'm sure I said something very inspiring, and he just sit down. But it's a good question. And, it wasn't just that, but that along with, my own kind of curiosity about the world inspired me to go back to graduate school. So I went and got a PhD in biophysics at Washington, St. Louis. And then 3 years ago, which seemed like a blur, started as a Truman Fellow at Sandia. And I'll say as a side note, these postdoc fellowships, Truman just being one of them, at the national labs are a really cool thing. You sort of get your own little mini grants to be the PI of your own project. And for me, it's been a tremendous experience. So if anyone is interested at a career level of just asking me about these sorts of fellowships, I'd be happy to talk to you and encourage anyone who's interested to go apply. So the big picture of that thing that I wanted to use physics to try to do is what I call sort of in a broad sense, the grand challenge of molecular model. And it goes something like this. Take any arbitrarily complex molecule. I care about biology, so this is the coronavirus spike protein, but you can put whatever molecular system that you are interested in here. And just ask, can we simulate this? Can we understand how this molecule moves, interacts with other things at the atomic scale? And, if you talk to people who are experts in this field of computational biophysics, will tell you, well, yeah, of course, that's a hard problem. Of course, you can't do that. But, maybe it's just my naivety, but I really like to remember that at the core, we have all of the tools that are necessary to solve this problem, right? We know F equals ma, which tells us how atoms move when we push on them. And we know how to get the forces that go into F equals ma to run this simulation, and that's by solving Schrodinger equation. But what I don't need to tell all of you probably is that the really tough part about doing this for large molecules is this part, right? Solving Schrodinger's equation for something with 10,000 electrons is basically impossible. What do I mean by impossible? So it's important to sort of delineate what I mean when I say that. There are algorithms on classical computers for solving the Schrodinger's equation, and various levels of approximation. One of the best ones is called coupled cluster theory. So what I'm showing you here is the time that it takes on a classical computer to solve the wave function or the density of this these systems of water molecules at the coupled cluster theory level. And you can see that, you know, doing this for small systems doesn't take very long at all. It's just like less than an hour. That's just over an hour. But you can also see that this curve is really taking off. So if you wanted to do this for 50 atoms, it would take like something like 2 months, and for 100 atoms, it would take 20 years. And, you know, we have a ton of patience as academic researchers, but we don't have that much patience. And if we want to do something with 20,000 atoms, then there's just absolutely no way. That's impossible. And just to underscore exactly what we mean by this, making this scaling possible, you might say, all right, well, that was just a cheesy test on your laptop. If you were at Sandia, you're part of the national lab complex, doesn't, you know, aren't we building giant supercomputers? And that's right. So if this is my laptop, this dot here, this very slowly coming in animation is the Summit supercomputer, which is no longer the fastest supercomputer. I'll replace this frontier. But okay, so let's say I want to do those same calculations I showed on the last slide on Summit. Well, okay, 100 atoms, how long would that take? All right, now we brought this down to 6 minutes, right? Our giant computer is doing this something. But if we wanted to do something like the coronavirus spike protein, the scaling really takes over again, right? And so the point is, we will never build a classical computer that is big enough to simulate the electronic structure of a protein. That's not something that will ever happen. And skipping way ahead of myself, I don't think that we will ever build a quantum computer to do this. There's intermediate physics that we're going to need to discover in order to make this attractive. So what I want to do, and should say, yeah.
Can you explain why DFT doesn't work for a protein of that size?
Why DFT doesn't work for a protein? Yeah, so I'm being a little loose with the terminology here, but the couple clusters stuff that all those numbers are based on scales is n to the 7, where n is like roughly your system size. DFT scales as cubic, and so even cubic scaling is going to be really difficult in the regime of a protein size thing. People have done DFT calculations on proteins, but the length scales, or the time scales that are necessary to understand any relevant property of a protein means that you're still not going to be able to do DFT calculations to solve that.
I mean, so you're really then hoping to find some algorithm that scales better than cubically.
Correct.
You're saying cubically isn't good enough.
That's right. Yeah, that's right. And so what we hope that algorithm may be is, I guess, just a hypothesis, is machine learning. So this is kind of this broad sketch of how this works, right? In a classical quantum mechanics calculation, you take your external potential, you feed that into your program, and it gives you energies and forces, right? What we'd like to do is to replace this with a neural network. And the reason that we want to do that is that at least if they're constructed appropriately, neural networks scale linearly with the system size. And so if you could adequately train this neural network, then you would have actually a chance of doing these sort of large scale simulations. Okay, so that's a general problem statement. We want to train a neural network to replace some quantum chemistry calculation, but what are the issues in doing it? Well, the first issue, and I think that the most important one to understand, is the issue of generating training data. So if I want to simulate this big protein here, I am stuck with a problem, which is that I cannot generate training data. There's no electronic structure data that I can get that has this entire protein, right? And so what people have to do is do fragmentation, right? You break this molecule up into smaller chunks, and then you do quantum chemistry calculations on those chunks, and then train the model based on those smaller fragments. But what you've done whenever you do this is you have imposed some sort of effective radius on, right? Machine learning is just a statistical method. It can't learn from things that it hasn't seen. And so that means that using a conservative estimate, the largest distance between any two atoms in my training set is 10 angstroms. That means that my model has an effective radius of 10 angstroms. The problem with that is that I didn't pick this particular protein out of thin air. This protein is called LOVD. It's implicated in cardiac function. And it's really well studied experimentally, including these mutations that are all noted here by these red arrows. And all of these mutations, what's interesting about them is that all of them directly affect the structure of this enzymatic pocket here, which makes the protein do its thing. And what's kind of interesting about this is that all of these mutations are more than 10 angstroms. Some of them are 15 angstroms. And I know that probably not everyone in the audience is calibrated on this, but trying to generate a training set that would have interactions up to 15 angstroms away and still represent chemistry in some sort of complete capacity is next to impossible, right? So the fundamental problem is, how do we include long-range interactions in our model if they're not in our training? Please.
So I think I'm confused about what the definition of a problem, because we started by saying we wanted to diagonalize the problem.
Yeah.
That's not what we're doing here, right? Because again, I don't see how the training data was. And then there was a point where it seemed like you wanted to do time evolution, and I don't see that either. So what is what is the problem? What are we?
Good question. So those are both good questions, just a little bit separate. So the first is we're doing Born-Oppenheimer molecular dynamics. So we're going to solve the electron structure of this protein with some oracle, and then get the forces from that, and then we're going to take a time step, and then we're going to do that all over. Right. So we're solving the time independent structure. The second is, you're correct, not going to diagonalize the wave function of this entire protein. What we're doing, sort of implicitly, by doing this fragmentation, is we're presuming some sort of locality, right? That the electronic structure of this part is independent from the electronic structure or the electronic structure. And that's the underlying assumption, right? So whenever you do fragmentation, that's what you have to assume, is that there's some sort of separability of the wave functions. Okay. Is that sufficiently answered? Yeah. Thank you. Okay. So I won't belabor this, but I'm not the first person to identify this long-range force problem as a problem in trying to do molecular simulation. So this is a really cheesy example, as opposed to my really complex one. These are just carbon chains, 2 hydrogens at the end. And these are a bunch of different machine learning models for energies and forces. And what they're plotting here is the energy as you rotate these 2 hydrogens on either end, right? So there's some energy barrier in the middle, and they're seeing, does the model reproduce that energy barrier? And what they see is the obvious thing, which is that once you get to long chains, where the chain is longer than the effective radius of the model, you don't see any difference as you rotate the chain, even though there should be some energy barrier there, right? So that's a much simpler example of exactly what I was saying before, which is that you can't have long-range forces in a force model if they're not in the training. Okay, so I'm going to propose a potential solution to this problem, and there might be others, but this is the one I'm going to try to convince you of today, which is that rather than learn energies and forces directly, which is sort of the standard thing to do in this machine learning for chemistry world right now, let's instead learn the electron density. And the reason that we want to do that is because I'm not going to change anything about my training data here. I'm still going to use the fragment approach. And so these electron densities will be independent objects, right? They will not be correlated to each other. But the difference is that I can use some classical physics, right? We know that once I have an electron density here and an electron density here, I can just use classical physics to compute a force between, right? And so this allows us, at least in theory, to get long-range forces, even if they're not explicitly represented in the training. Okay, so that leads to the second problem, which is a pure machine learning problem, which is that The machine learning and electron density is a much different task than machine learning and energy, which is one number per configuration, or some classification tasks, which are all things that we know machine learning can do very well. The density is a scalar field in three-dimensional space. And that means it has a bunch of symmetries, right? Like the most obvious being that if I rotate this density, it's still the same thing, regardless of what state I've rotated them. And I just want to take a second to sort of underscore what the importance historically of including symmetry in machine learning models has been. So many of you will have heard of ImageNet, which is a big classification competition where machine learning models are submitted to try to identify whether there's a dog or a cat or whatever in the picture. But what you might not know is that ImageNet has been around for a really long time, long before any of us probably were aware that neural networks exist. The thing that really put it on the map was this, I think in 2012, I can't remember exactly, model called AlexNet, which included this new operation called convolution. And I say new in scare quotes here because it had been around for a long time. We just didn't have computers big enough to actually build these models. And convolution is this like simple idea that you take a patch and pass it over all the pixels of your image, and it encodes some like locality. The information, but the thing that it does in practice is it imposes a symmetry called translation invariance on the model, right? And translation invariance is key to pictures. If I have a dog on this side of the picture and that side of the picture, it does not matter, right? There's still a dog in this picture. And so it was by including translation invariance that machine learning models really made that leap to being really incredibly accurate for image recognition. And so what I've tried to do in this project is build in the relevant symmetries that are important for electron densities. So I have to give a bunch of credit here to Tess Schmidt, who's a new professor at MIT. She's, among others, one of the inventors of what are called Euclidean neural networks. And I'll just briefly describe what they are and why they're, I think, the right tool. So Euclidean neural networks are graph convolutional neural networks where every atom is represented as a node in a graph, and each interaction between atoms is represented as an edge. And then we pass that graph through subsequent layers of a neural network, applying nonlinearities along the way. And this is all in 3 dimensions, even though my schematic here is. What's different about Euclidean neural networks, or E3NN, is the implementation that we work on, is that rather than in a traditional neural network where the features on each of these, the hidden features, I should say, on each of these nodes is just a list of scalars, and then we apply operations on those scalars. In E3NN, the features on nodes are combinations of spherical harmonics, right? And as chemists and physicists, this should give us warm, fuzzy feelings, right? This is the way that we like to represent data signals in space. And by having this inherent structure where the features are combinations of spherical harmonics, and by only applying operations, i.e. Clebsch-Gordan coefficients that preserve the rotation symmetries of these objects, we get this property of equivariance, right? And equivariance just means that if I have some object in a rotated version of that, the network sees them as the same. As a kind of cheesy example of that, if I train an E3NN network to recognize Tetris pieces in their sort of canonical orientation like this, and then I test it on these rotated versions, you get the exact same accuracy on the test set as you do on the train set. So a whole lot of math to do something that's really very simple, which is just to recognize rotated objects as the same. It turns out that this property of equivariance isn't just sort of a nice to have thing for learning in electron density. It's absolutely essential. So this is just a really simple sort of toy example, but if I train a network to recognize the electron density of just one water molecule, and I train 2 different networks to do that, an equivariant network and an invariant network, where again, this invariant network just has scalars on the hidden features of the graph. If I then rotate that water molecule and test on it, I get the 0% error on all of the rotated versions for that covariant model, but an invariant model has big errors that are dependent on the rotation state. So at the risk of making the obvious here, you really need equivariance in order to get this property.
Could you tell me a little bit more how you
so given this graph, how do you encode this set of harmonics to the graph?
Yeah, that's a good question. So this is, let me make sure that I understand the question correctly. So in the first layer of the graph, each node gets just two scalars, and that's just a one hot encoding for whether you're an oxygen or hydrogen. Then in the subsequent layers, which this could be n number of hidden layers, when you construct the network, specify how many hidden features of each type you would like. So this is saying I want 10 scalars, 3 vectors, and 2 rank 2 tensors. And that could be the same for every hidden layer, or it could be different. But that's the structure that you specify. These are just saying what is the object feature that I would like. It does not tell you what the magnitude of any of those is, right? The magnitudes of those are then determined by the training of the network, right? Which has parts that I won't go into, but is constrained to give you these features with those spherical harmonics on each.
So is this correct? Do you have more expressibility on your model or kind of parameter to train?
Yeah, that's a great question. So we think, although we cannot say conclusively, that for n number of parameters, if you compare an invariant model and an equivariant model, that the equivariant model is more expressible. I'll show you data for that. It's a great question. Yes.
When you train your invariant model, did you train it with rotations from your input data? I mean, that's what I would do if I only had access to an invariant one, right? And rotate it 100 times or whatever.
Yeah, you're absolutely right. So the thing that is done, and is done commonly in machine learning, is that's called data augmentation, right? And there are things to be said for data augmentation, right? Like the idea of machine learning is to not impose, to not have to impose too much human knowledge as we can on a problem. What we have shown conclusively is that you eliminate the need for data augmentation with equivariance. And in some fields, that may not be doing data augmentation may not be a big deal, but generating training data from quantum chemistry calculations is very expensive. And so
rotating it, right? You get your output from whatever couple cluster, you could rotate the electron density.
It's a fair point. I think that the argument that I make and others make too is, if you have this equivariant model at your disposal, what advantage does doing data augmentation still have? Okay, so just to not to put too fine of a point on it, here's the big picture of what we're doing here. So we're using a Euclidean neural network as our surrogate for the quantum chemistry calculation. We're generating the electron density from that network, and then we're going to use classical physics to calculate forces on atoms from that density, i.e. the Helmholtz line. Okay, so I'll go briefly through the next couple here. The first thing that we wanted to do is figure out, does this actually work? In other words, is an equivariant network expressible enough to learn an electron density? And the short answer is yes, it is. So if you train a model on 500 samples of the electron density of 8 water molecules, DFT calculations as your training data, you can get a model that has tiny differences. This is some randomly chosen member of the test set, and you can see that the differences in terms of number of electrons here are quite tiny. If you integrate across the entire test set, your accuracy is less than 1%, 0.25%. Or the error, I should say, it's less than 0.25%, which is as accurate or more accurate than other density models. Getting to your question about expressibility, what we found is that the inclusion of high angular momentum features in the hidden layers of these networks is really key to getting the data efficiency that we see. So let me sort of explain what's going on in this. So I trained 5 different networks here and tested them across a range of training samples. So this is what's called a learning curve. So this is number of training samples on the X and accuracy on the test set on the Y. And let me explain the difference in what models to train. So these here explain what the representation in the hidden layers is like. So for this Lmax equals 0, for instance, this is just an invariant model, right? This is only scalars in the hidden representation. For Lmax equals 1, we have scalars and vectors, Lmax equals 2, so on and so forth. All of these, importantly, are equivalent size, right? All I've done is reallocate some features from one channel to another. I haven't made the network bigger. What do you see? This is on my L equals 0 network here. And as I continue adding higher angular features, both the slope, sort of, and the absolute accuracy shift down. In other words, they get more accurate. Let me just point out a sort of example to make this point. So a model here that's trained with an Lmax equals 2 network gets about the same accuracy with 100 training samples that a network with Lmax equals 0 gets with 10,000. Right, that is a huge difference in expressibility. And it's really a function of what the nature of these hidden features is.
So while the number of parameters staying constant here, I mean, it's actually doing operations take the same amount of time here. Like, if I imagine that going to larger L will cost you in actually having to do computation.
Yeah, great question. It takes a lot longer. Yes, as you add higher L, it takes a lot longer.
Do you have a sense of like what that scale?
That's a good question. I should and I don't. I also sort of punt on that because there's a lot of software engineering that we like to do to try to make it faster. So it's kind of comparing apples and oranges at this point. But suffice it to say, you're something around an order of magnitude for each of these, maybe a little bit less. Yeah, but that should get better with time if the benefit of this model is really that good. We should be dumping a ton of effort into making it. All right. So I'm going to skip this actually. So the thing that we wanted to do is, all right, we have a model that is expressible enough to learn an electron density of a molecular system, right? What about our motivating hypothesis, which is that we want to be able to train on small systems and get models that are reasonably good on this. So to test this, a grad student that's been working with me, CQuiC, came up with a kind of clever experiment. He put together 7 different training sets of increasing sizes of water clusters. So this is 7 waters, 8, 10, 12, 15, 20, and 25. And then trained models on each of those, and then tested those models all on the same test set, right? That's the 30 water molecule test set, which is sort of the biggest that we do. And here's the data from his experiment. So this is error on the y-axis. This is the training set size, physical size of the training set on the x-axis. And you can see 2 basic phenomena here. The first is that at these low cluster sizes, like 7 and 8, as you make the cluster bigger, you make that model more accurate, which makes sense, right? 8 water molecules looks more like 30 than 7. But the thing that's really interesting is that you reach a plateau, right? Somewhere around 12 water molecules-ish, you no longer make the model any more accurate by making your cluster trainings, the size of your training clusters any bigger. And what that's saying, you think, is that around a radius or a diameter, I should say, of about 7 angstroms, you've already included all of the relevant information that the machine learning model can pick up to tell you about what the density at any given location of that cluster is. And that's pretty cool, right? Because 7 angstroms is not very big in terms of chemical systems, right? And that's a really interesting observation. It's also sort of yes, please.
How would this compare to the accuracy if you just took your test system, cut it up into cubes or spheres or whatever, size 7 angstroms, and ran a couple cluster on each of those cubes to get the density?
Yeah, that's a great question. We haven't actually done that test yet, but that's that's something that we've been dying to do because that sort of answers the locality hypothesis that we're really trying to get at here. are some new, we should talk later about that because there are some nuances that make that not exactly an apples to apples test, but good question. One thing that we wanted to do was sort of do some sanity checks on this to make sure that we're, saying something reasonable and that it's not hard. So we did a second experiment, which was to exactly replicate what I showed you on the last slide. But instead of training on electron densities, now we're going to train on forces, the conventional machine learning or chemistry way. And if you do that, what you see is that you don't see plateauing behavior, right? As you make the cluster size bigger, if you train on forces, you continue to make the model more accurate. That's interesting, right? That's a fundamentally different behavior than the density itself. The last thing that we did is to compute Hellman-Feynman forces from the model density that I showed you on the last slide. There's no new training here. These are just models from the previous slide, but now I'm computing Hellman-Feynman forces from the densities that were predicted in the from those models. And what you see is that the forces calculated from the Hellman-Feynman theorem follow roughly the same behavior as the density itself, which is suggesting that what we're seeing here is real. The density is kind of vocal in the way that it appears to be on the from the data. So let me give you yes.
Yeah, sorry. I might just be missing something simple here, but if you look at the Y scaling, it's plateauing, but above where the scale on the left, you still get a better.
Yeah, you're not supposed to look at my slides there. Yeah, so these are details that are relevant, but it takes a minute to explain. So when you do a quantum chemistry calculation, you use a basis set to discretize the space. Current basis sets that are used in quantum chemistry are do a very poor job of calculating Hellman-Feynman forces. There are big errors that are incurred because of the nature of how basis sets are constructed. So what I'm doing here is not the calculations here. This is only the long range component, which is I've carved out a sphere around each atom of I'm not going to remember that it's something like 10 angstroms are in that neighborhood. And I'm calculating the forces on the force contribution beyond that sphere. And so that means that this is a different force calculation. Yeah. So what we'd really like to do is to recreate this, but with the full forces by solving this problem with quantum chemistry basis sets so that we can do full Hellman-Feynman forces. All right. So let me just sort of give what I think is the interpretation, my interpretation of what's going on in this data. I think what this is showing is that if you want to use a machine learning model to make the best possible prediction that you can of the force on some given atom, you need to include training data that goes up to 13 or more angstroms away, right? That's what the data on the previous slide was showing. But if you want to do the same thing for the electron density at some given point around that atom, our data is suggesting that you only need training data up until 7 angstroms away. Insofar as, because size scales cubically, the difference between these two is practically from here to the moon, right? This, you would never be able to train a model in this regime, but that is feasible, right? We can generate clusters of atoms that have a radius of 7 angstroms. Yeah.
How specific to something like water do you use?
No ideas. I'll show you some data on DNA later that suggests that it's not that different. But okay. Yeah, doing some systematic study of this in different environments, different temperatures, different body
Related question. So, how can I build confidence? Let's say I'm interested in one specific one. Just this one.
Yeah.
And I don't care about the average thickness. I really care about this specific. How should I put this type of observations?
Yeah, that's a good question. I think it really depends on whether the molecule that you're studying is sort of in an environment or not, right? So if you just want like a gas-phase model of some small molecule, then something that you could do a quantum chemistry calculation on, then this actually has no, this does not offer any hope, right? Because the whole point of this is to get long range resistance. But if you want that molecule solvated, say in a box of water, right? Then this is where that comes into play, right? Because you know that you are going to have long range effects for solvation. Now, as to how you ensure that you get, you know, specific energy barriers of a rotation or something like that, that really boils down to your training. And you have to, there's something magical about these models in terms of statistical learning, right? You still have to really intensely sample the areas that you want your model to be very accurate in. And there's, you know, nothing here will change the need. Does that sort of answer the question?
Yes, but also, so the motivation was that we know that there is a Q method, and maybe we can do it with scaling of that. But then the training, the time that take the data set that I need for training and the time that is for training, it might be the case that it's not clear that look at the whole package and the scaling of that will be better to the Q versus training.
Yeah, I see what you're saying. Yeah, that's still an open question, right? It's how general can training be? Training has to be very specific for every new system. Then much of the benefit of this is lost. And yeah, I actually don't have a lot to say on that. There are people doing interesting work, sort of characterizing chemical states. And that's sort of an orthogonal direction to what this is. We're characterizing physical states, right? Like how far away is this interaction? But you know, how complex is your environment is a whole other thing. And that's, you know, just something that I can't say whether it will be worth it or not for humans. All right. So let me just add a little bit more physics motivation to why I think there's this difference between training on forces and training on density. I think that it's there's a simple sort of perturbation theory argument that can explain the difference here. So if I think about two interacting molecular systems, say in two waters, you can think of a whole spectrum of perturbation going all the way from, all right, density of this to the fully correlated electronic structure. And if you were to write this out in some sort of like rigorous perturbation theory quantum chemistry way, the very first order in perturbation would be electrostatics, right? That would just be unperturbed density of A interacting with unperturbed density of B. And then you would get further interactions coming in at higher orders. And so what I think this is saying is that at this 7 angstrom boundary, this first term is dominating, then the rest of these are falling off, right? That's saying that, all right, I can calculate forces without having the full correlated interaction. I think this is, you know, maybe a step too far, but, you know, or it could come to me here, I hope. I think that this is what is kind of neat about this whole thing is that usually in the machine learning world, we're training things that are black boxes, right? We're training a model that is used as a surrogate, and then we forget that the original was there. But what's kind of neat about this sort of experiment that we've done is that we're actually getting at what, you know, is some tough physics to understand without machine learning, which is this idea of how nearsighted is our electrons in molecular systems. So there's this famous paper, The Nearsightedness of Electronic Matter, from back in the 90s, I think. And it actually, if you look back at that paper, defines nearsightedness precisely in terms of density perturbations. In other words, if I'm some point here, nearsightedness is determined by what is the radius beyond which any perturbation to the potential does not change my density, or only changes my density by epsilon, right? And so what's really neat is, you know, in a very indirect way and with lots of caveats, you know, that's exactly what we're doing here, right? That's exactly the sort of observation that we've made. So I'm not trying to say that I've like solved nearsightedness of electronic matter, but there is kind of a window into it, I'll say, that machine learning gives us a unique tool to do. I'll wrap up by kind of giving a nod to some application areas, or an application area. So we've taken to doing this similar scheme with that we've done with water on DNA. So again, we want to replace an expensive electron structure calculation and build a surrogate model for the electron density of DNA. And this is, I should say, work that is done by a postdoc, Alex Lee, who's over in the chemical engineering department. And he can do some really cool stuff. So this is a piece of DNA for which there's an actual physical crystal structure. And this is our machine learned prediction of the electron density of this actual crystal structure of DNA. And it turns out this is pretty accurate. Compare that with the DFT calculation. The differences here are pretty minimal.
So what was the training data?
Good question. So yeah, basically here it was less systematic than with water. Alex took molecular dynamics simulations, classical molecular dynamics simulations of DNA, cut out 2 base pair steps, and then did DFT calculations on those 2 base pair steps. He can also do cool things like calculate the electrostatic potential, because of course you can get all this information from the density. And these electrostatic potentials are really accurate. You could potentially use them for some sort of bio engineering or biophysics uses. For instance, people tried to predict where a drug will bind in this like minor groove of a piece of DNA by the electrostatic potential. That's pretty neat. It's not exactly the same or as rigorous as what I was showing before, but Alex sees a very similar size extrapolation behavior to what I see, which is that he trains on these 2 base pair steps, that's this here. But if he takes that model that's trained on 2 base pair steps and then tests it on 3 base pair steps, or 4 or 5, the error in those predictions does not go up almost at all, which is suggesting that he's capturing all the locality that he needs to just in that 2 base pair step. This is one we don't know yet. Just a good question. So, this again is much more the goal here is applied rather than just try to understand the nature of correlation. But it's funny you asked that because Alex has tried to take that same training set that he had and break it into smaller chunks so that he can train it faster. And so far, it seems that he can do that without losing much accuracy at all. So it seems initially, at least, like 2 base pair steps was kind of overkill. This is kind of a fun way to wrap this up. So these are our calculations that Alex did with our machine learning model on huge structures of DNA. So this is a 10 base pair, I think, or more Drew Dickerson decamer, which is the canonical DNA. This is they have stacked holiday junction, which is relevant to DNA nanotechnology applications. And over here is the nucleosome core particle, which is actually the spiral of how DNA packages itself in our cells. And I just think this is cool. This has close to 10,000 atoms in it. This is so far beyond the realm of what could ever be done with a quantum chemistry calculation that it's even tough to fathom what that would take. But with a reasonable model on a reasonable GPU, you can do this in under a second, which is just really cool, right? There's nothing mind-blowing about that, right? We know that machine learning models have this linear scaling capability, but it's cool to see it in practice. All right, so I'm going to sort of wrap up with some conclusions and then give just a little takeaway here. So 3 things I think I'd like for all of you to take away. The first is that any model that's serious about wanting to do large-scale simulation with machine learning has to be able to train on small and right? You have to be able to train on fragments because there's no other way. Second takeaway is that using Euclidean neural networks to learn an electron density is probably a pretty good way to do this. I think the data that I showed really supports that this is a promising direction to be able to solve that first thing. And this works, at least so far as we can see, for water and DNA, yet to be determined for other systems. And I'll just wrap up by saying that, this is a quantum information group. And one thing that I think a lot about, though it's not in any of this work here, is how will we use a quantum computer for quantum chemistry once it comes to fruition? And I'd like to say, I think I've said this to a couple of you, that I don't think that it will ever happen, that we will use a quantum computer to simulate an entire protein on its own. That is going to be very difficult to do, even with the most optimistic projections of current hardware. And B, more importantly, I don't think it's the right physics, right? I don't think that it's the best thing to do to brute force that. And the reason I say that is because there is inherently some physics that we're missing in this concept of the nearsightedness of electronic matter, right? This, is only sort of brushing the surface of that. But some version of that is going to have to be how we use a quantum computer to do these large simulations. Right? We're going to have to whether it's machine learning or something else, discover or write down the rules of what locality is, so that we can effectively use a quantum computer even once they're built and can be used for a reasonable number of atoms. So with that completely unsubstantiated statement, I'll just wrap up by thanking folks at Sandia and collaborators that contributed to all the work on the slides, and thank all of you for your attention.
Josh, great talk. We have more time for questions. Sure.
I kind of have a generic question. So I think a lot of times you were comparing what you got with machine learning with results with DFT and stuff. But I guess like you always have another kind of doubt that like, is DFT also like actually true or not? So I guess like ultimately, if you can have some kind of like comparison with actual experiments and stuff, then that'll be like the true answer, right? Like, because that's eventually that's what you want to predict. So like my very generic question is like, are there any kind of systematic criterion that like, if you can compare with experiments and get those right, so you can say that like you are really on the right track kind of thing?
That's a great question. So 2 levels to that. The first is that coupled cluster data, while is not quite the level of true experimental data, has been much more validated, I guess, for small systems. And a lot of the water data that I showed you, I recreated with coupled clustering, and the accuracy is very similar. So there's no like hidden boogeyman there. I am very interested in doing the real comparison. And the first way that comes to mind for me to do that is to compare with X-ray crystallography. So X-ray crystallography measures the density directly, and at least for things that are low temperature and not floppy, those would be really great. It's difficult because the level of resolution on those experimental measurements is quite low compared to infinite resolution quantum chemistry. But that shouldn't stop us from trying. I would love to do that.
I see. But basically the bottleneck here at the moment, I guess, would be the experimental resolution.
For X-ray crystal data, you could envision other ways that are less direct. For instance, if we get the Hellman-Feynman force things sorted out, and we can use machine learning to predict the density and use the density to calculate forces, then we could do MD and then calculate thermodynamic properties from a molecular dynamics trajectory and compare that to experiment.
I see.
That's a couple layers of indirection.
Right.
So you
also add MD as well. Okay, I see.
Yeah, but that's the other one.
Excellent. Thank you.
Thanks.
Yeah, kind of similar to what you're saying about calculating forces. What if you were to somehow, if you were able to calculate forces correctly, but you thought correctly, could you train against protein structure that was calculated from, say Google's network or whatever, right? Say, here's 1 million proteins. This is what the ground state is. We know that there's not going to be any forces in this ground state. does our model predict there are no forces for this configuration? And if not, let's improve it using that as some kind of like, loss.
Oh, that's my grand dream. Is that so? This AlphaFold model that you're referring to, it's this tremendous tool, right? It gives you a prediction of any folded protein. Wouldn't it be cool if, in addition to that, one static structure, you could have simulation data on each of those? And yeah, that would be incredible. That would be a Herculean effort, to be sure, because of the amount of training data that would be necessary for all that. But the other thing that would allow is all of this is trained on some level of quantum chemistry. We would learn a lot about how accurate some of these are, right? We don't know if you were to do a DFT PDE0 simulation of a protein, whether it would be good. So.
Okay, a question on the mentioned how there might be you might have sort of loose perturbation theory, such as explanation or some of these indices. And then you mentioned how it's you're looking at this expansion and then you're saying, okay, some of these terms presumably get smaller. Have you done any computational work showing that they like getting these extra terms, they are appreciably smaller, confirming this perturbation theory explanation here suggesting?
That's a great question. The short answer is no. It relates directly to your question about whether you've done a couple clustered calculations of each individual subsystem and then stitch them all together. And that is sort of the nuance that I was alluding to before, which is that they're not completely separate subsystems, because you're going to calculate classical forces and energies between those subsystems. But yeah, we haven't done it yet, but would like to in the near future. Good question.
Any other questions?
Do you have any rough estimate of the quality of your 1 second GPU calculation?
Yeah, very fair point. I mean, that's the tough thing about doing these very big. I mean, the answer is no for that one. We have no idea. So all of the validation work that we're trying to do is sort of like at the far leading edge of how far you can push a classical quantum chemistry calculation. Because beyond that, with the exception of experimental.
Yeah. So
if we
can you crystallize that?
Yeah. The short answer is yeah. There's a ton of crystal structures out there. The problem is it's very low resolution, right? So any model is probably going to do okay. We don't know yet, so I guess we'll have to see.
And sort of more broad philosophical question. I mean, this thing talking about was learning physics, like learning new models.
Yeah.
What do you see as the future of like learning such heuristic models of machine learning? Because we're not getting out any like equations anymore. We're not even getting out these like we learned before, like fluid dynamic, empirical equations. There's no like simple compact form, right? We just have this neural network that train on some data and then we feed it some more data and get some predictions. Like, is that how we're going to learn empirical models in the future? Like, we're going to write formulas anymore. Or formulas dead.
Necessarily. Let's say that this project that I don't know either of your names, sorry, but both of you in the back have suggested trying to do the like 7 angstrom localized calculation. Let's say that we do that and it works spectacularly well, right? Well, then that does suggest a new algorithm, right? Of saying, I have learned what the level of appropriate coarse graining is for water, right? That is a new, decoupling equation, right? But that's some new closed form physics. Okay. I am skeptical that it will be that clean. Sure. But I think that it's by poking around at these things that you kind of find it, right? It's very unlikely that we would find it on the first try. But I guess philosophically, I don't believe that's it. I think that there's still possibility to learn new closed form things that is not just some statistical, right? Downside.
This time, Josh. Yeah.